Federated Adversarial Cross Training, FACT, is a novel approach to federated learning that addresses the challenging scenario of adapting a model to a target client without access to annotated data. FACT leverages the implicit domain differences between source clients to identify domain shifts in the target domain. In each round of federated learning, FACT cross-initializes a pair of source clients to generate domain-specialized representations, which are then used as a direct adversary to learn a domain invariant data representation. The authors propose FACT as a solution to the limitations of traditional federated learning methods, which assume i.i.d. data and struggle with distributional differences between clients. FACT's adversarial strategy allows it to adapt to the domain of an unlabeled target client by directly evaluating interdomain differences between source domains, eliminating the need for concurrent access to both source and target data. The FACT training scheme involves cross-initializing two source clients, which locally optimize the model and broadcast it back to the server. The server then aggregates the generator and shares it with the source clients for fine-tuning of the domain-dependent classification heads. The classification heads and the global generator are then sent to the target client for interdomain distance minimization. Finally, the optimized generator is broadcasted back to the server, and the classification heads are aggregated for the next round of federated training. The authors empirically demonstrate that FACT outperforms state-of-the-art federated, non-federated, and source-free domain adaptation models on three popular multi-source single-target benchmarks. FACT also outperforms state-of-the-art unsupervised domain adaptation models in single-sources single-target experiments. The authors further study FACT's behavior with respect to communication restrictions and the number of participating clients, showing that FACT benefits from additional source clients, is stable with many source clients, and can be efficiently applied in settings with communication restrictions. In the realm of federated learning, unsupervised federated domain adaptation, UFDA, has garnered significant attention, particularly in scenarios where data is distributed across multiple clients and lacks labels. UFDA aims to enhance the out-of-distribution performance of a model on target data without access to training labels. Recent approaches have focused on federated adversarial domain adaptation, source-free domain adaptation, and multi-source partial domain adaptation. However, these methods assume centralized data or rely on augmented training samples, which is not feasible in federated settings. This work addresses the federated multi-source single-target setting, where data is non-i.i.d. and distributed across multiple clients. The authors propose Federated Adversarial Cross Training, FACT, a novel training scheme that leverages interdomain differences to maximize information transfer to an independent target domain without labeled data. FACT involves a global server managing the training process for a set of local source clients and a target client holding solely covariate data. The motivation behind FACT is to learn a domain invariant data representation by exploiting interdomain differences. This is achieved by evaluating whether a sample is generated by the source or target distribution and suppressing domain-specific features. The authors define the interdomain distance, IDD, as a measure of covariate shifts, which is minimized to enforce agreement between target estimates. The FACT algorithm consists of three main steps: source training, source fine-tuning, and target interdomain distance minimization. In the source training step, two randomly selected source clients are cross-initialized with the global model, and each client updates the local models. In the fine-tuning step, the classification heads are optimized to fit the frozen feature generator. The target interdomain distance minimization step updates the feature generator to minimize the IDD. The author's approach is inspired by adversarial learning strategies and the maximum classifier discrepancy (MCD) adversary. However, FACT differs from MCD in that it does not require concurrent access to both source and target data, making it suitable for federated learning applications. The proposed method is simple, efficient, and can be applied to various domains, including medical imaging, where multi-institutional collaborations are common. Here is a combined summary of pages 5 and 6. The authors propose a novel federated domain adaptation method called Federated Adversarial Calibration Training, FACT, which leverages interdomain distance minimization to mitigate domain shifts in multi-source single-target scenarios. The method involves fine-tuning the classification heads of individual source clients and aggregating the updates to the global feature extractor, followed by interdomain distance minimization on the target client. The authors evaluate the performance of FACT on 3 benchmark datasets, namely Digit 5, Office, and Office Caltech 10, using various state-of-the-art baselines, including federated and non-federated domain adaptation models. The results, presented in Tables 1 and 2, demonstrate that FACT outperforms the baselines in most scenarios, with an average target client accuracy of 95.2% on Digit 5 and 88.7% on Office. The authors also analyze the behavior of FACT in different federated learning scenarios, including the effect of suboptimal source data, the number of participating clients, and the number of communication rounds. The results show that FACT is robust to negative transfer and can adapt to different numbers of clients and communication rounds. The implementation of FACT is based on PyTorch and is publicly available. The authors use a ResNet 101 architecture and a batch size of 128. With a learning rate scheduler proposed by Gannon et al. The results are averaged over multiple repeated runs to ensure convergence. The authors highlight the advantages of FACT, including its ability to handle multi-source single-target scenarios and its robustness to domain shifts. The method's design allows for practical applications, as it can speed up training by reducing the number of trained epochs and client communications. The authors also discuss the limitations of FACT, including the increased communication costs associated with fine-tuning the classification heads. In this study, the authors introduce a novel approach to domain adaptation in federated learning, named Federated Adaptation with Class-Wise Alignment, FACT. The proposed method is designed to address the issue of domain shifts between source and target domains in multi-source single-target federated learning settings. By aligning the class-wise distributions across different domains, FACT aims to improve the generalization capabilities of models across various domains. The authors evaluate the performance of FACT on 3 different datasets, Digit 5, Office, and Office Caltech 10. They compare their approach with several state-of-the-art baselines, including MCD, M3SDA Beta, FADA, and FEDCA. The results indicate that FACT consistently outperforms the competing models in most scenarios, especially in cases where there are significant domain shifts between source and target domains. Notably, the fine-tuning step in FACT improves model performance, particularly for challenging target domains. Moreover, the authors demonstrate the robustness of FACT with respect to suboptimal source domains and its ability to handle a large number of clients efficiently. They show that adding more source clients does not significantly impact the target performance, suggesting the applicability of FACT in scenarios with many sources. Additionally, they study the performance of FACT under communication restrictions, observing that the accuracy remains stable even with as few as 25 rounds of communication, although the performance of more challenging target domains decreases gradually. The findings from this research contribute to the advancement of domain adaptation techniques in federated learning, providing a new perspective on how to handle domain shifts and improve model generalization. The proposed approach can be beneficial for real-world applications where data distribution varies widely across different domains. Here is a combined summary of pages 9 and 10 of the research paper. The proposed approach, FACT, achieves state-of-the-art performance in multi-source single-target domain adaptation, even in federated scenarios where direct data exchange between clients is prohibited due to privacy concerns. FACT combines 2 objectives: minimizing a standard classification loss and minimizing interdomain distances. This approach substantially outperforms baselines in most experiments, even when the data is distributed across multiple source clients or when server communication is restricted. The authors demonstrate the effectiveness of FACT through various experiments, including varying the number of participating source domains, splitting individual source domains across multiple clients, and restricting communication rounds. The results show that FACT achieves high target client accuracy even under restricted communication. Despite its simplicity, FACT is a highly efficient and competitive approach that can be valuable in many real-world federated scenarios. However, the authors acknowledge some limitations, including the lack of theoretical guarantees for the applicability of FACT in different scenarios and the requirement for sufficient resources to calculate gradients and transfer large models between clients. The authors also provide a comprehensive review of related work in domain adaptation, federated learning, and unsupervised domain adaptation, citing papers by prominent researchers in the field. These references include works on dynamic regularization for federated learning, unsupervised multi-source domain adaptation without access to source data, and practical secure aggregation for privacy-preserving machine learning. Overall, the proposed approach, FACT, offers a promising solution for multi-source single-target domain adaptation in federated scenarios, and its simplicity and efficiency make it a competitive approach in real-world applications. However, further research is needed to address the limitations and assumptions of FACT, including the need for theoretical guarantees and the requirement for sufficient resources. This section of the research paper discusses various aspects of federated learning, domain adaptation, and privacy-preserving machine learning. It begins by citing several studies on federated optimization and its applications in distributed machine learning, 17, 18. The paper also references works on domain adaptation without source data, 19, 20, which is crucial for scenarios where access to the source domain is restricted. In addition, the paper explores multi-source domain adaptation, 32, 49, where multiple source domains are utilized to adapt to a target domain. This is particularly important in real-world scenarios where data distribution varies across different environments. Furthermore, it highlights the significance of privacy-preserving techniques in federated learning, 30, ensuring that sensitive information remains confidential during the learning process. The paper also delves into the concept of domain generalization, 48, which aims to train models that can perform well on unseen domains. This is achieved through techniques such as feature distribution matching, 40, and adversarial training, 41, 42. Moreover, it touches upon the issue of negative transfer, 44, a phenomenon where the performance of a model degrades when adapting to a new domain. The research also covers the use of gradient matching for domain adaptation, 47, which aligns the gradients of the source and target domains to enhance model performance. Moreover, it discusses the importance of conditional adversarial domain adaptation, 38, which utilizes adversarial training to align the feature distributions across different domains. Lastly, the paper mentions the development of frameworks like PyTorch, 31, which facilitates the implementation of these complex methodologies. Overall, this section provides a comprehensive overview of the challenges and opportunities in federated learning and domain adaptation, emphasizing the need for robust methodologies that can handle diverse data distributions while maintaining privacy. In the context of multi-source domain adaptation, this research paper presents a novel method for addressing the challenges posed by varying source distributions and target labels. The proposed approach, known as Federated Adversarial Domain Adaptation, FADA, leverages the principles of federated learning to facilitate collaboration among multiple sources in order to enhance target domain performance. The paper begins by outlining the limitations of existing domain adaptation methods, which often rely on a single source domain or require access to target labels. FADA overcomes these limitations through its unique architecture, which consists of a shared feature generator, multiple source-specific classifiers, and a target classifier. This setup allows for the simultaneous adaptation of multiple source domains to the target domain, while also promoting knowledge sharing between sources. To evaluate the efficacy of FADA, the authors conducted experiments on 3 benchmark datasets: Digit 5, Office, and Office Caltech 10. These datasets were chosen due to their diverse nature, encompassing both digit recognition and object classification tasks. The results of these experiments demonstrate that FADA outperforms state-of-the-art methods in terms of target accuracy, highlighting its ability to effectively adapt multiple source domains to the target domain. The supplementary materials provided offer additional details regarding the implementation of FADA. Specifically, the paper outlines the model architectures used for the feature generator and classifiers in each dataset, as well as the hyperparameters employed during training. For instance, the feature generator for Digit 5 consists of 2 convolutional layers followed by max pooling, while the classifier consists of 3 fully connected layers with dropout and batch normalization. Similarly, the Office and Office Caltech 10 datasets utilize a pre-trained ResNet 101 as the feature generator, with a two-layer classifier for classification. The paper also includes a detailed table summarizing the number of samples in each dataset and domain, which serves as a valuable resource for researchers seeking to replicate the experiments. Additionally, the supplementary materials provide a table detailing the target accuracies obtained by FADA for all possible source-target combinations on the digit 5 dataset, further emphasizing the adaptability and effectiveness of the proposed method. Overall, the research presented in this paper contributes significantly to the field of multi-source domain adaptation, offering a novel approach that leverages federated learning to enhance target domain performance. By providing comprehensive experimental results and detailed implementation details, the authors have established a foundation for future research in this area. The table on page 15, Table 7, presents the number of classes for each dataset used in the research. This includes Digit 5 with 10 classes, Office with 31 classes, and Office Caltech 10 with 10 classes. The datasets are crucial for understanding the performance of the proposed method in various scenarios. Table 8, also on page 15, provides the target accuracies obtained for the standard single-source single-target UDA setting for all possible source-target combinations of the Digit 5 data. This table highlights the performance of the model across different datasets, such as MNISTM, MNIST, SVHN, SIN, and USPS. The results indicate varying degrees of accuracy, ranging from 29.0 plus or minus 2.52, MNIST to MNISTM, to 99.17 plus or minus 0.04, MNISTM to MNIST. These findings are significant as they demonstrate the efficacy of the proposed method in adapting to different data distributions. On page 16, the authors discuss the importance of domain adaptation in deep learning. They emphasize that despite the progress made in this field, there is still much to be explored, particularly regarding the theoretical foundations of domain adaptation. The authors propose a new perspective on this problem, which they believe could lead to further advancements in the field. In summary, the 2 pages provide an overview of the datasets used in the research, the performance of the proposed method across these datasets, and the author's perspective on the future directions for domain adaptation in deep learning. The tables and discussions presented in these pages are essential for understanding the research's contributions and its implications for the field.